Thank you. Thanks for coming. Before I talk about my contribution, I think it'll be useful to provide some context. So concurrent revisions is a concurrency control model by Burkhardt and others. First paper stems from about 2010, but there's some follow-up work on it as well. And so these kind of models help you deal with concurrency. It has some nice high-level properties or interesting properties. So in particular, it has a nonlinear program state history. Conflicts, you do not avoid them like you might do with locks or rollback in case of conflict, as you might do with transactional memory, but you in fact resolve them at runtime. And the model also does not have any data races. There are implementations in C# and Haskell, and a lot of the papers are quite pragmatic in that respect. But for our purposes, more interesting is that there is a formal semantics from 2011 with informal proofs of certain properties of this model. And so what I did is I formalized part of these semantics in Isabel Hall. It's been available on the archive for formal proofs for a while if you want to have a look. So let's start with some basic concepts of this model. The central unit of concurrency is revision, which you can think of as a task or a process. And each revision is identified by some identifier, which is part of the program logic. A revision has a fully isolated store, and also all computation takes place within some revision. And these executions you can visualize using revision diagrams. So here we have a revision R1 on some empty store, and it's computing some expression which I do not show. So what can you do in this model? Well, first of all, revision can perform some local computational step. 0 is assigned to X. It's very boring. But then there are two synchronization operations. The first one is the fork. And when the revision forks a task, it creates some new revision, which inherits a copy of the forker store. And also the identifier, R2, is exposed to the forker. So it's part, like I said, of the program logic, and it can, you can do things with it, as we shall see. Now we have two revisions running in concurrently, so they can be run in parallel and they can be scheduled non-deterministically, so that's where your parallelism comes from. But then at some point a revision terminates, and what you can do then is you can join the revision if of course you have access to the identifier. The effect of this is that the joinee ceases to exist, and the joinee store is merged into the joiner store. Now, clearly you have a conflict here, so the question is, how would you resolve this? And in this model, semantic type annotations are used. So rather than saying X is an integer, you say, for instance, that it is a versioned integer, where the meaning of versioned roughly means accept the changes of the joinee since the closest common ancestor in this revision diagram. So in this case, we would accept the 2 here, and X will be 2. You could also have, for instance, a cumulative integer, which says accumulate changes since the closest common ancestor. So maybe X is kind of a counter, both added 2, and then the value will be 7. And the versioned one you might want to use, for instance, if it's a higher priority task. And the idea is that you, as a programmer, you can define your own isolation types and their own merge functions. Just declare them somewhere, and then in the application logic, you don't have to deal with the merging. It will happen automatically. Now, these revision diagrams, this fork-join behavior can grow quite complex. So this is a valid diagram. So R2 forks R3, sees its identifier, and you can think of it as flowing along this line. And then later, R4 can join the R3. But despite this complexity, CR is a determinate model, so the result of a program execution, of course, assuming some conditions like you don't allocate random numbers, the result is always the same. And this is the main theorem in my formalization. I will say something about a result that is lacking later. And also what I did is formalize all the preliminaries that are needed in this paper proof. So before I say more detail about the semantics, let me tell you how the state of a revision is encoded. So we definitely need at least an expression in the store, as we saw from the preceding. But orthogonally, what we have to solve sometimes is we have to find the store of this closest common ancestor, because it may have a role in the merging process. And rather than building this graph on the fly and doing reasoning and trying to find this ancestor, the following is used. Note that of the joinee, the store it started out with is the exact same as the store of the closest common ancestor. So there is this result that this first store of the joinee is the store of the closest common ancestor. So this is something that could still be formalized, and it's not part of my formalization. But this is used in the semantics as follows. The state of a revision is now a triple. It consists of this snapshot, a local store in which updates are tracked. So these two stores are the store that we saw earlier, and then just the task expression that it is computing. So here is an overview of the operational semantics. There are 9 rules. And you don't have to understand this. I will just tell you what I found. So first of all, rule fork has a side condition that should be more strict than what is formulated in the original paper. And these 3 rules involving storing values, they contain redundancies in the side conditions. So I will show you this now. First of all, rule fork, well, you have to allocate revision identifiers, and you need some notion of freshness, because definitely you cannot allocate these revisions over here. And the side condition concerns this notion of freshness, and this is how it's formulated. So the allocated revision identifier is not mapped by the global state S and does not appear in any snapshot or local store of S, which under my interpretation means it's not anywhere in this orange part over here. Then I wondered, it seems to specifically exclude the expressions, so I wondered if this would be problematic, because if you would arrive in this scenario where an Rx is joined that is not anywhere in this orange part, so it's dangling, then you would have a threat to determinacy, because if this Rx is not allocated, then in the semantics you collapse to an error state because the join is not defined. And if this Rx happens to be allocated here, then you have a join that can proceed. So you do not get the determinacy result. Question is, of course, can this scenario occur? And in my paper, I show a short trace where you see that this scenario is actually possible. And my fix then for this side condition is to say it doesn't appear anywhere in the global state. Maybe this was the original intention, I'm not sure, but based on the formulation, I thought this was the direct interpretation. So what about rule new? So rule new is used to store a value under a fresh location identifier, and which you can just think of as a memory address. So here, V is stored and a reference will be returned. In this case, it's an L. And also here, the side condition has a similar phrasing, so it's not in any snapshot or local store of the global state. I wondered, what about dangling location identifiers? This one is going to join R1. If this one allocates LX, the read will succeed, and otherwise it's blocking in the semantics. So again, you have a different normal forms. And I tried to find a counterexample because it seems quite symmetric, but this scenario is actually not possible because of an invariant that the location identifiers in E are a subset of the domains of these stores. So that means whenever you want to work with a location identifier, it will have been allocated in your local state. So to summarize the original side conditions, where these are the informal formulations of or representing the informal formulations in the original count, we have the following situation. The formulation of the side condition and new can be weakened, as we just saw. Get and set, these are side conditions for reading and writing a location, but by the fact that you're reading or writing it, you know it's allocated because of my invariant, so you can get rid of this side condition. And most importantly, this side condition of fork needs to be strengthened. So this was kind of the preliminary examination I did of the specification. And then I moved on to determinacy. All right, I should mention that these findings actually do not seem to carry over to the implementations because Haskell and C# are, they just use the object creation mechanism in those languages and the garbage collection. So in particular, if you have a reference to something, it will not be allocated in these languages. Okay, so determinacy. So this statement is, of course, modulo renaming equivalence. For any initial state, all the reachable terminal states are renaming equivalent. And as a standard way of proving this, it suffices to prove confluence modulo equivalence, which is also what the original offers do. So this is the many-step relation. And my proof follows quite closely the proof of the original offers. So let me explain what my proof looks like, and then I will talk about the comparison. So let's first consider single-step divergences. It turns out that, there are 9 rules, so 81 cases for the steps, half of which are symmetric. But you can show that they can always join again in one step. It's called strong local confluence. So in the formalization, quite a lot of work went into handling all these cases. And then you can just do diagram tiling where we need this small change over here. So for confluence then, again, it's quite a standard proof with strong local confluence. For this particular example, you can tile like this. And then you have to complete the square over here. So it would suffice if steps can be simulated for equivalent states, which I call mimicking diagram. This is not in the original count, but you need this to complete this square over here. So you do this, you figure out this part, and then you get confluence modulo equivalence when you generalize the relations. All right, so what does the original confluence proof do? Because they also have to deal with these equivalences. What they do is they lift the original relation to a relation over equivalence clauses modulo equivalence. So from here, we go to this. Of course, proving confluence for that diagram property is completely standard. Just do it like this. And the original proof then concludes that confluence modulo equivalence follows from confluence of this lifted relation. So it's quite intuitive, but from how exactly would this work? So if you here have a reduction on equivalent states, it might look like this underneath. So it's disconnected steps over these equivalence clauses. And when I was formalizing, I originally went with their proof. I wondered how I could complete this. That's how I found this mimicking diagram, because if steps can simulate, then you can get this reduction. So this approach, this lifting, unless there's some other proof, doesn't actually seem to help much. You need this mimicking diagram together with this strong local confluence. So to summarize, the technical findings are that, well, I think the specification of the operational semantics is cleaned up a little, so this definitely needs a strong formulation. These you could loosen up a bit. And I also found a bit easier and a complete proof of this determinacy. And in general, the contribution is really a case study. I don't think I used any methods that can be easily generalized to other proofs, for instance. But it could also be a foundation for possible extension of this model. And like I said, there's still much left to formalize of this original paper. In particular, these properties about these diagrams, they are a bit intricate. So what they do in the paper is they build these diagrams on the side, and then these proofs on these graphs are also quite intuitive, or they use intuitive reasoning. And formalizing that is seemed like quite a lot of work. Jasmine actually made a start with it, and we might complete it as well. Thank you.
Okay, we have a lot of time for questions. Yeah.
Although it probably wouldn't have saved you a lot, but I wonder whether you tried to use results from the René Thiemann's ISA4 formalization of the rewriting, of the abstract rewriting.
ISA4 formalization?
He's got a large library for rewriting formalized in Isabelle.
Okay.
So you didn't?
No, I was not aware of that.
Okay,
It was actually my first time using Isabelle. Yeah.
Right, yeah. So, and I wondered how well that library would have stood up when somebody tried to use it.
Yeah.
Any more questions? I have a question. So when you have a conflict, you need to merge these two branches, so that a conflict resolution operator has to satisfy certain kind of a property in order for the whole thing to be confluent. Is there some condition you imposed on that? Or?
So in the original work, I didn't get to show it here, but in this revision calculus, they only use the versioned merging that we saw earlier.
Okay.
And they discuss some generalization of this in their paper. And I think that it would work if there are no identifiers in the condition on this merge operation.
Okay.
But it's not part of this formalization.
I see. Do you have a plan to find out what are the requirements for the merge operation in order for the whole thing to determine it?
So in the direct future, it's not a plan to continue this work,
okay.
but I might do that later, yes.
All right. Thank you very much.
Thank you.
Any more questions? All right, let's thank the speaker again.